everyone, and welcome to this very first presentation event. I'm so pleased to see that so many of you was able to join us today because we have Du-Ikonen, and he's about to give us a presentation about fault detection of machines using sound processing. Welcome to us. Very nice to have you.
Thank you for calling me here on stage. Good afternoon, fellow signal processing enthusiasts. I'm very excited to be here to present my topic here for you today. Let's start by looking some numbers. Average cost of downtime is about $260,000 per hour on average in all industries. And this is on average. Of course, the costs depend on how big the industry is. For example, much bigger industries like paper mills or oil production, the cost could be higher, but it could be also lower in some other businesses. Often these faulty machines cause the downtime in a manufacturing plant. Therefore, it's very important to use sound detection or all other possible fault detection methods available. Let's start looking at some video about noises, fault detection by noises.
Hello, I'm Thomas. We are here at Technobotnia. Today we are testing out fault detection of electric motors based on sound. And we have a test setting here that we have two motors here. One of them is has a bearing fault and another one is normal. So let's start first by listening to the voice of the motor, and let's see if we can recognize which one is the faulty motor and which one is the normal motor. So we have two almost similar 2.2 kilowatt electric motors here, and each of them have the same kind of frequency converter here. And the setting for this is 25 Hz. So let's start from motor 1. Okay, that's a sample from motor 1, and next we'll try motor 2.
So could you hear the difference? How many people think that the motor number 1 was the faulty one? Please raise your hand. And what about motor number 2? Okay, that's everybody then. Could somebody explain why the motor number 2 sounded like it's faulty? Yes?
It was correctly. The sound wasn't so clear.
Yes, exactly. As you can see, it is very easy for our human ear to detect these kind of failures that are coming, but for machines it's more difficult. This motor eventually it would have failed and failed completely, and after that it would only reach full speed if you throw it down from the roof. Okay, here's the structure of my presentation. So I'm going to tell about the background, about the sound detection or fault detection based on sound, and then I made my own experiment, and I also compared my results to the results that I get from literature. And here are all the sales story. So when I started introducing myself to this topic, I started by making a literature review. I found a master thesis from halt University about this topic, and I found also several other scientific publications about the topic. The topic is quite new. I'm not aware of any practical implementations of this, but there are some material available about this. There are different approaches to prevent downtime in general. First, we have preventing faults. Basically, it means scheduled maintenance. We have statistical information about every machine part, how last it would last. For example, this kind of electrical motor bearing is at 400,000 hours, and after that, it's going very likely to fail. The downside of this approach is that the engine part could fail earlier than the estimated time. And also in some critical applications there are this kind of very high security buffer. So you're going to change the part long before they are going to even do a fault. So this brings also extra expenses. So you change parts more often than you really need, than it's required. Detecting faults is this what we are here what we are addressing here. There are also other ways to detect faults from electric motors. Methods based on the vibration. There's a sensor attached to the shaft of the electric motor, and there's also methods based on acceleration. Other methods could be like a gas leak detector or a fire alarm. I've implemented in my automation design often this kind of feedback loop from the relay contacts. So the relay contacts are connected back to the input of a PLC, and then we compare the start command and the actual command that comes from the coil, because these relays they often fail. There are like dozens and hundreds of them in an industrial plant. So even though it takes a little bit more time on programming and wiring the system, but on my experience it's very it really pays off, because you can fast detect these kind of faults, and detecting like single this kind of relay it could be. But there are dozens of other things that could go wrong. And third is to design fault tolerant systems. Basically, you just design the machine to be so durable that it doesn't fail. On one biogas plant I was working with, there was a pneumatic compressor that failed, and some of the valves that were in the biogas plant were controlled by the pneumatic system, and of course when the pressure goes down, the plant is basically down. It doesn't work, and just because of the compressor failed. So you could also design the system in a way that there's like two compressors side by side, and when the first one fails, the other one comes, detects this and starts and keeps the pressure on the system. This would be an example of fault tolerant system. Each of these approaches have their drawbacks, and the best results are achieved when you utilize them all together. When we start to analyze the sound, by signal processing, it has to be first digitalized. So it has to be recorded and digitalized in a form that a computer can understand this. And these are common mathematical methods that we can use to process the signal. For example, there's a moving average filter. It makes the signal a little bit more smoother, and this way maybe we can detect the actual signal that we are trying to look for. This could be used, for example, filtering background noise. Gaussian filter, its impulse response is a Gaussian curve. In some applications, it could be useful. Other method is a bandpass filter. So if we know that this background noise works on a certain frequency, we can filter the signal in a way that this background noise is filtered out. Discrete wavelength transform, it means that you change the amplitude and the phase of the signal in a certain consistent way compared to the original mother signal. And it's possible to resample signal. For example, if the sampling rate is too low, you can add more samples, and the added samples are compared to the neighboring samples, and it can be interpolated by using the neighboring samples. Or the sample rate could be also lowered, and in which case you just remove some of the samples from the signal. Often it's very important to choose a window size. For example, in this moving average filter, and this window size it's usually a couple tenths or hundreds of milliseconds, but it really depends on the application, what you are trying to get from the signal. What kind of window size could be best. Root means square amplitude, because this kind of waveform it changes from plus to minus, and if you take an average of it basically becomes zero. So this addresses the problem of the negative signals and could be useful in some applications. Some of the features we want to see from the signal could be a zero crossing rate, because it's the amount how much the signal changes from plus to minus, and how many times it crosses the zero line basically. Or amplitude variance. Here's an example. The left graph has a high amplitude variance, and the right graph has a low amplitude variance. Here are some examples of the features that we want to, or could want to examine in time domain. Here's a formula of short time energy. The lower formula is for discrete signals, and the top one is for continuous signals. So the discrete signal is like a limited signal from limited space. It's the start and the end. Where the continuous signal, it just goes on and on to the infinity, like the construction site of polyglot tree. It is often very useful to examine the signal both in time and frequency domain. So here's just a very basic example of how it works. So imagine we have this basic 50 Hz sine wave, and then we have another 1000 Hz which has a lower amplitude but a higher frequency. And when we sound these together, it would become the black signal there. Okay, I'm going to remove the two earlier signals to make it more clear. But imagine a situation that we, of course in this simple situation we can already see the dominant frequencies in here, but the real signals are much more complicated, so we cannot see it. But if we want to extract the frequencies that are here, we use the fast Fourier transformation. There's a formula for it, and the result would be like this. And from the right graph, we can clearly see the 50 Hz and the 1000 Hz peak pointing out of them. And we can also see the amplitude. So the higher frequency in this case has a lower amplitude. From this frequency domain, we are interested. We could be interested about these features. For example, it could have like tens or several hundreds of frequencies, and they would focus on some part of the graph. With a spectral centroid, you could find this out. Or if it's very divided, the spectrum, you could find it out by spectral spread, or it could be flat. There are all kinds of mathematical methods to analyze the signal. In my work, I focused on electric motors. The most typical bearing fault is the electric motor fault is the bearing fault. So that's responsible of 51% of the faults. And another common type of fault is a low current or a high current. I mean, which and it is caused when the insulation of the windings are degraded, and it's often because of excessive heat. Here are current solutions for detecting this kind of bearing failure. Operator basically hears it when he walks in the plant. Okay, this motor makes a funny noise. And there's also a vibration and acceleration based methods, and these are already products that are used in the industry. The benefit for this sound-based analysis, it's much more cheaper method. Microphones are basically very cheap, and they don't require direct contact to the motor. So they are easier to install. So basically, you could install this kind of microphone in the general area. Ideas alone have little value, and innovation's importance lies in its practical implementation. This quote is from founder of Siemens, which is a Q2 company from Germany. So after reading the literature, I started experimenting on myself. And I placed two objectives for myself: detect faults before they occur, and I wanted to evaluate the viability of this sound-based detection. So I built this kind of test setting in Technobotnia. I called to ABB and asked if they would have this kind of extra motor with bearing fault. Well, they didn't have that kind of, but they were very interested about my experiment. So they break one bearing for me and send it to me in the name of science. And then I get two frequency converters and all the similar all the motors and frequency converters were as similar as possible to eliminate all the things that could interfere with the experiment. Then I recorded the sounds using the methods we have learned in this course, and then I processed the data, and I found some methods from the literature, and I used MATLAB to implement them. So first, when I started recording the faulty motor, for some reason, first 3 seconds was distorted. I don't know what is the reason for this. Maybe it was the microphone, my computer, but I first thing what I did for the signal, I just extracted the first 4 seconds and the last second from the signal, and it became like this. And the same thing was done also for the normal motor. And I did fast Fourier transformation for each signals and plotted them. And we can clearly see in the top right corner that there's this kind of 3300 Hz fault frequency coming from there. If you compare the faulty and normal motor, there the frequency spectrum is quite similar, except the amplitude is much higher for the faulty motor, but it has also this fault frequency. And in the literature, they could also get like similar results. So they get 2 these kind of extra frequencies popping out from the frequency domain. And my conclusion is that this sound-based method for fault detection is feasible. It can be, for sure, can be implemented by using this sound analyzing, and possibly then we can send an alarm to the automation system to alert the personnel or the operators. Limitation, according to the literature sources, is the background noise. So in my test setting there was no background noise, so it was quite easy for me. But the challenge for others was this. What was the background noise? If you want to develop this as a product, we need a lot more testing to if we can detect what happens when there's background noise. Often these industrial plants, they are very noisy places, and also different kind of faults. How would the system react to this? It would be very important that the sound-based fault detection system would easily recognize the faults from there, but it shouldn't be too sensitive either, because this makes the operators very numb for the alarms. If they all the time hear alarms, then they don't anymore react when there's a real alarm. And it should be, of course, easy to use. Technology should make our lives more easier. Otherwise, it is not feasible. In some of the methods, they collect samples from different kind of faults, but there are so numerous solutions where sound detection could be implemented that it would take too much time to collect all the possible fault samples from all the possible examples we could have. So my idea would be to use machine learning applications to detect these kind of abnormal frequencies or features from the sound. Because I'm aware that it is possible with machine learning to detect these kind of abnormal signals even without teaching this to the system. Then I would like to send a special acknowledgements to ABB who supported me with this motor, and also the employees in VAM who booked me the laboratory and helped me to do the experiment. Here are some references that I used to do this. Thank you. Now it's time for discussion.
Thank you, Thomas. If it's okay, I would like to ask some questions.
For sure.
Yes. I think this was very widely explained already, but do you think we are able to identify what kind of fault is about to happen? Do we know about the sound which one is going to break?
Most likely not. If we use this kind of machine learning approach, then the system will probably. Okay, there's some kind of new kind of fault, but I think that would be enough. Then we can react to the problem, and maybe we can record that to the system. Okay, this time it was the pipes were clogged or something. That's why the motor couldn't move. And this way the machine learning could be continuous. But detecting all the possible faults, I think it's impossible. At least we should start with the most common ones.
Do you think, are you aware that someone is already using this kind of method in industry or somewhere else?
No, I'm not aware of this kind of sound-based detection. I have never seen this in business, and I couldn't find it also in the literature.
Yeah. Okay, so I'm interested about those weak points. You already mentioned that one limitation is the background noise, but is there anything else? I was thinking that maybe could we set faulty alarms easily? Or is it extra work? Is there such a risk?
Yes, that was the first thing that came into my mind, that the system would be too sensitive and make a lot of false alarms. If I would develop this kind of system, I would start with very high threshold. So the signal has to be very strong before it makes the alarm, and also it would have to be continuous, like it would have to last for hours or days, and then the system makes the alarm. Okay, maybe there's a bearing fault.
Yeah. Also, I was thinking that if we would have this kind of method, how would it record the sound, and would the sound be maybe saved somewhere? Is there any risk that a person who is working in a factory is doing her or his daily job and having some private conversations, and the system would record those private conversations in somewhere? Is it any risk?
That's a very good point. I didn't think of that, but we should surely address this thing also. I think that the recording shouldn't be required to be continuous, so it would be enough to take maybe a couple of samples, short samples in a day, also to save space for recording of sound. This would solve the problem only partially, but maybe the recordings should have some kind of information security policy, so it wouldn't be available just for anyone. So we want to protect the information, not to protect the people's personal data.
Does anyone have anything more to ask?
Well, yes, I have one question about the, you mentioned about the vibration and the sound. You can use both to detect those faults. Could they be like implemented together? Like, for example, there is like vibration detector, and then the sound in the microphone, and they are combined. Like, if there is some kind of background noise that is extreme,
Yes.
and like that, so they compared that there is no vibration, but there was some kind of spike in the microphone. Is that like the case? Do you
Yes.
see that it would be implemented?
Yes, it could be possible, and it would make the system much more reliable. But we have to remember that the advantage of using sound detection is the cheap price. So we don't want to necessarily to use this vibration detection only for the most critical machine parts.
So it's much more expensive to use the vibration.
Yes,
detection.
I would suppose so.
Okay.
Did you run the motor with constant speed all the time? Like, did the input voltage be 50 Hz all the time?
The first experiment was constant 25 Hz, and the second experiment it started from 0 to 25 Hz. I recorded that also, but I didn't process the signal just to keep things simple.
Yeah.
Just for this kind of demonstration purposes, it was enough.
You said the noisy environment is the limitation. What about the opposite? If it's too quiet, the motor, what do you think, is that also a limitation?
Could be also, and for some machine parts they don't make sound at all, so it could be possible. On the other hand, one advantage of sound detection compared to the vibration and acceleration is that it could detect like leaking pipes if there would be that kind of extreme case. Or I'm sure that there are other examples also that can be detected by sound that are not available with other, but for sure it has its own applications, and it's not suitable for everything.
Any more questions? Okay. I think I would now give my feedback. I can see you were very well prepared, I think. I think we all can see that. And the fact that you were so excited, it also made me very excited. It was very fun. You sent the material in advance, and we also already had the conversation by email, and you already asked me to give some feedback, and I did. And it was really very nice to see that you actually already improved the presentation by the feedback I already gave, and also you already answered a lot of questions by email. I think that shows that you are putting a lot of effort in this. I was so impressed that you actually had those motors. That was so nice. And also you had those motors, and you had the recordings, and you had processed those signals, and you were actually able to show us the faulty signal in there, and I think that was really great. I think the structure of the presentation was okay. I think it was much more clear now when I saw it actually. Yeah, I think those slides where there was just the right amount of text and material. Yes. Yeah, I think maybe you were a little bit nervous today. I was too. I think from time to time you were able to relax, and I see that you enjoyed presenting, where you just a little bit relaxed in there. Yeah, I really enjoyed the show. I think you did a great job. Does anyone have any more comments? Okay, I think we can finish this. Thank you very much.
Thank you for the feedback.